Hello, everyone. My name is Nieswandt. I'm the European Product Marketing Manager for Vision Products of Omron in Europe. And today I would like to welcome you to my home office. I think as many of you, we are working from home nowadays, but still try to keep up the close communication to our customers. So today, thank you very much for joining this live event about AI vision tools on the Omron FH vision system. Today, I want to give you an impression on how Omron makes the powerful artificial intelligence technology accessible to a wide range of users. Unfortunately, I will not be able to promise you a solution for all your vision inspection issues, but I'll show up some ways how AI technology can help you to gain line productivity. Having a quick look at the agenda first. To begin with, I want to quickly explain the principle of vision inspection systems in general, and explain our opinion why AI tools can be a meaningful addition to that. AI in vision, like other technology trends, is not an end in itself, but should always deliver customer value. This is followed by the introduction of the two AI-based vision tools that Omron features on the FH vision system and the target applications they are aiming for. To underline and demonstrate the true added value and therefore the success of the implementation, I'll share some internal test results comparing AI versus the traditional approach. After that, we will connect to our vision expert in the automation center in Barcelona to give you a look and feel on the usage of the actual tools. This is followed by a quick summary about what AI can and cannot do. The live event is closed by a Q&A section in which I will try to answer the question that you can put in the comment function on the right-hand side. So let's get started. Industrial vision is not a new topic. It has been implemented decades ago. From the early days until today, tremendous developments have been made to keep up with the demands of various industries. So today you find high-speed applications with very reasonable cost price, very reduced size, so space consumption of these systems, and in general with a very high accuracy if you have the right setup. The general principle has not changed much. After the image acquisition, the vision software offers a possibility to set tolerances for the acquired image results, allowing the extraction of individual not okay parts from the material flow, or the activation of countermeasures to avoid production of bad parts even before they happen. So traditionally, you would be able to measure dimensions, count objects, check for present absence, or make shape comparisons. Even with the latest inspection technology, many applications still require a high skill level and much time to set up, and it can only and some applications can only be handled by human optical inspection. This is especially the case when you deal with very complex objects or production line that see a high product mix. Also, products with a high natural deviation or product-related deviation represent a challenge even today. In this example, you see, for example, a PCB board where there are many different objects present, and you can imagine if you would need to check them one by one, it is a very labor-intensive way to, or very labor-intensive job to set that up. Also for applications like a soldering application where there is a lot of influences and you cannot really determine the final result, you will have natural deviation in the test part you need to check. So in this simple example, you find an object. In this case, it's a battery. If you look at it from above, with a natural deviation in the center circle structure. This natural deviation makes it very challenging to recognize defects in this area. As you can see in the sections highlighted with the red rectangulars, the circle in the middle, the circle structure is not a perfect shape, but has some dents that would possibly be judged as not okay parts by a traditional vision system. So this challenge comes obviously with negative effects. The number one, and I think worst case, would be that a defect part is not detected reliably. On the other hand side, if you set the tolerances too narrow, you could run into a high rate of falsely rejected parts that also would be waste or additional effort in the end. And as mentioned before, a very high engineering investment is needed to keep the inspection system running and updated. So you need an expert on the line to adjust if you have deviations within individual batches, even of the same product. And finally, and I think this is also still reality today, many inspection processes have been done by humans. Looking at the performance of a production line, we find and analyze different production batches. In this case, production 1 and production 2. If you break down the results further, you can identify different phases with values for the key indicators, line output, and quality level. The first phase, indicated in red, is a changeover time. That is needed to make necessary adjustments for the general setup of the line. The phase 2 is the setup itself. It is needed to get the production for a new batch up to speed and batch-specific adjustments made. The phase 3 is the actual core production. It represents the actual production process at target levels for output and also quality level. This is obviously a simplified model, and every operator or line manager can set the values of their specific case by themselves, but the goal should be common everywhere. Expand the core production phase and minimize the losses during the changeover and setup time, because this is the time where you lose money and productivity in your production line. So the sooner you are able to get your line up to speed and producing at target quality, the more productive your line becomes. A better inspection quality could also result in less rework cost or the reduction of additional visual inspection. So again, our promise is not to solve all your challenges with AI, but to provide you a powerful tool to optimize your production line step by step. You will be able to gain speed, you will be able to improve the quality and also gain stability for your production. So let's have a look how we want to achieve that and how, let's say, an AI model is built up in general. I will spare you with any detailed explanations about artificial intelligence and how it works, let's say, deep inside the system, but just give you an overview about how the use case for our tool is actually constructed. In the phase 1, a testing model is created by feeding real product pictures into the tool. They need to be marked as okay and not okay. Based on this, a virtual testing model is created. In the phase 2, the actual production is started. The incoming pictures are tested against the model and evaluated as okay and not okay. So as you can see, a very straightforward process. But obviously, there is pros and cons to everything. The, let's say, main advantage you can find with using such a system is that engineering time can be reduced, over-detection can be avoided, complex tasks can be solved relatively quickly. You can operate the system with the limited expert knowledge, and you can potentially replace manual visual inspection. On the other hand side, such a testing model is more or less a black box if you compare it to the traditional approach, where you can set tolerances and also in the step further document them for any quality inspection purposes. And again, here the documentation settings of the settings can be difficult. Many solutions out there require high processing power or special hardware, and in the end, if we are honest, still expert knowledge is needed. And for sure, it is not a fit for all applications that are out there. So how did we approach from Omron's side this topic? We still believe in the well-proven and well-trusted high-performance capabilities of a traditional industrial vision system. But we wanted to provide the real capabilities and true advantages of this technology to a wide audience, but not as a standalone, but as an addition to our well-proven FH toolbox. So for the first step, this funneled into 2 additional tools that are provided with our FH software. Number 1 is the AI fine matching tool, and the number 2 is the AI scratch detection filter. Both tools will help you to reach even better results in a shorter time frame. Looking at the AI fine matching tool, again, it's a 3-step process. First, you need to prepare and upload the pictures, both good and non-good pictures, into the tool. Based on that, the AI algorithms create an AI model, and as a third step before you start the production, check result step is implemented. So before you start, you can validate or make even small adjustments towards the inspection task that is supposed to be handling the production. Looking at individual cases, again, we use the same model. In case 1, we have an okay picture. The input image is both judged right by the conventional model and the AI fine matching. In the case number 2, you have a new defect type that has not been known before. Since with the conventional model, you would not search for such a defect, it will also be not detected. You might have a chance that it is somehow in the scope of what you are checking, but it is not reliable. With the AI fine matching algorithms, you are able to detect even defects that have not known before. In the case 3, we have a product with a natural deviation. So when you look at the conventional method, there is a chance that this natural deviation is judged as a defect, even if it's a perfect fine product. So there is a great likelihood that you have a false defect and you sort out a perfectly fine part. And this is really the strength of the AI fine matching, because it takes all the natural deviation that you teach during the implementation process to the tool. It takes this into account and does not indicate a false defect here. In the case number 4, there is a defect in the deviation zone. And maybe based on your findings in case number 3, you limit your ROE, your area of interest, you limit it to a certain area. So whenever that area is not on top of the defect, you will miss it. With the AI fine matching, again, this is a clear, okay sorting result, as you can see in the pictures. So as a summary, what's actually the benefit of the AI fine matching? First of all, and that's really important for us, it is part of our standard toolbox. So it's not a standalone library that you somehow have to implement into your vision system, but it's running on the device, it's running on a standard controller, and it's a very intuitive use for anyone that is familiar with AFH. Again, you can use this as part of the standard workflow and use it with standard vision tools that have been, let's say, dominating the inspection world ever since. So the AI fine matching can contribute to a significant reduction of engineering effort and time needed to, let's say, find a reliable solution. On the right-hand side, on the top, you can see, let's say, conventional inspection flow versus an AI fine matching flow, and all the individual filtering for defect A, defect B, defect C. As long as it goes, you can replace by one simple fine matching tool. In some internal tests that we have performed with our Omron colleagues, we were able to document a setup time reduction of 73%, with reaching 100% correct inspection results. So I think this is very impressive and a good indication about how capable this tool can be. Looking at target applications, obviously it can be used inline, but also end-of-line inspection, especially in cases where product properties cannot be measured. So where there's some kind of hurdle or difficulty to express the property of a part in numbers. You cannot, put, let's say, a millimeter value or an area value into a special property of the product that you need to inspect. Also, in production or inspection cases where unexpected and new defects can happen randomly, the AI fine matching really plays out its value. Also, when you have very complex shapes to inspect, or productions with a high and frequent changeovers, like we see in the food and commodity industry quite a lot. And in general, if you have, let's say, reduced resources of skilled workers, the AI fine matching can really make a difference. So in order to give you an impression on how it works, let's play a quick application video of the live system running. Here you can see, let's say, how the individual, in this case, connectors are inspected. You see the natural deviation, so there's not one connector looks like the other one, but you still get a very reliable inspection solution. The second tool I want to introduce, and this is even more simple to use, is the AI scratch detection filter. This tool is based on a pre-trained neural network and is specialized to detect scratches on homogeneous surfaces and backgrounds. So as you can see here, even the, let's say, slightest scratches, and you see the, let's say, actual picture on the left side, and then the result of the tool on the right side, even the slightest scratches are enhanced, and then you are able to, let's say, extract and analyze the resulting pictures. This is really, let's say, a fire and forget tool. So it is also fully integrated in the FA inspection flow. You just have to place your ROE, so your area of interest, over the area you want to inspect, and it operates basically by itself. So it also allows you to combine it with traditional image filters to even, you know, pre-process or post-process the picture to get better results. But in the end, it makes it very easy for you to benefit from AI technology with just a drag and drop tool. Again, here, looking at the target applications, definitely for cosmetic inspection of finished goods that can be found maybe in the glass industry. Also, any kind of consumer electronic devices with a monitor. This is where we typically see these applications and these challenges provided by us, to us by the customer. Also, any painted or polished surface is a perfect fit for this tool. Again, also here we made internal tests with Omron colleagues, and here the time reduction is even greater. So as I mentioned, it's a drag and drop procedure, and it is connected to a 91% reduction of setup time compared to a traditional approach, again with 100% correct inspection results. So enough for now from my side. Now I want to give you the true impression about the look and feel about how to use these tools. And for that, I would like to connect to my colleague in ATC Barcelona to give us a quick overview about how the tool and the operation really is performed on the FH controller.
Thank you very much, Jan. So I'm Enric Cornellà from ATC Europe at Barcelona, and I work as a vision system specialist there. So I will try to explain in a little bit more detail how these two tools work.
So let's start with the first tool, which is going to be the AI fine matching. What we are going to try to do here is inspect this LED here, which has some faults. So we are gonna start by adding it on the flow, and you can see there are some defects here that we are gonna try to spot with this AI fine matching tool. Right now it's on no good because it's hasn't been trained already. The first thing to do is select the right images. I already have them on the quick access, so there's an OK folder and a no good folder. So what we are going to do is we are going to give the category of OK and no good for each one of these sets, so the algorithm can understand which are the good images and which are the bad ones. The next step is to set the measurement region. In here, what we want to do is to tell the algorithm where to look for defects, or where to learn in this case. So we're going to start by learning as a circle and all this part that is inside. I'm going to select a few images here to start initial training. What we want to have is a good representation of images, so it can create a kind of a golden sample. And from this golden sample, this is going to be our model. And this model is going to be compared with new images that are coming, and it's going to be classified in OK and no good images. This step now is optimization. So it's going to tell us how we are classifying the images. So you can see on the background how the algorithm is running them one by one. And at the end, it's going to show us a little table where we will be able to see if we are judging the images as OK or not. Our final goal here is that all of them are identified correctly, right? So we want the OK to be OK and the no good to be no good. So as soon as I click OK here, we are going to go to the results. So we have 55 correct, but still 57 that are not. That's already quite good, right? So we used only 4 images, and with these 4 images, we are already identifying 55, but it's not good enough. So let's go one step further here. I'm gonna classify the images and pick the ones that are like wrongly classified. So I'm picking these 6 images here, and I'm gonna add them on the learning data set. So now you can see here I have much more images. So I'm going to execute the learning again. So creating my model. This is a process that's quite fast. And okay, just takes a few seconds. Again, I will go to the optimization step and try to optimize and see if we are getting better. So hopefully our 55 images should be a much larger number now. And we'll see if this is true or not. This process should be repeated as many times as it requires. Usually between 3 and 4 times is enough to do the whole optimization work properly for the image. So we'll see here, okay, we have 104 images detected as correct, but still 8 that are not properly labeled. So I'm going to speed up here the thing. Just don't want to take a lot of time. So there are a couple of cycles more I do here just to try to optimize it properly and have everything working fine. So, okay, going back from the pause now. And we should see that finally we are able to detect all the images properly. So let's see now if the parameters are fine. So we have 112 that are correct. And okay, 0 miss, 0 false, and 0 error, which means that okay, finally we are able to segment properly the okay from the not good images. Which means that our model has been properly trained. So just for double checking, I will run the no good analyzer. I'm going to load the images here. So I'm going to select the folder where I have all my okay and no good images. I'm going to execute the batch measurement, which means measuring them all. And okay, we should see here how we have okay images 100. The no good images are 12. And this means that okay, the okay images were counted as okay and the no good as no good. So we are doing fine with 100% accuracy on both the okay and no good inspection. Let's go now with the second tool, which is the AI scratch detection filter. This is under compensate image. And this is much more easier than the previous one. Simply just apply the scratch detect filter. We have to set the region of interest, which okay, now by default is already taking all the image. And basically that's all we have to do. We just now look at the result and maybe use some kind of a labeling tool or a blob tool to try to find these scratches, which the AI scratch detect filter is already emphasizing for us. So at the end it comes quite easily to spot this after the detection filter has been applied.
So I hope you understood these new tools. Thank you very much for listening, and we're going back to Jan. Thank you.
Yeah, thank you very much, Enric. Very impressive. Also, yeah, how it's, let's say, integrated in the standard AI, or within how the AI product is included in the standard workflow. Very impressive. To sum up this session, I want to quickly summarize where we think what AI can do and what it cannot do. So where are the possibilities, but also where are the limits? As you have seen, the tools are part of the inspection flow of the standard FH product. So it can be, we make this technology accessible for a wide range of users without needing to really care about what AI is and how it works. It runs on the standard FH 2050 and 5050 hardware. So it's a well established product with literally tens of thousands units running all over the world. So you really can rely on very proven and very established hardware technology here, and still take advantage of the latest technology from a software point of view. Again, you can freely combine it also in the workflow with traditional vision tools. So if you just want to, get the additional additional comfort of adding or checking, one specific property of the product with the AI tool, and the rest you rely on the proven traditional vision approach. The mixture is possible anyway. And finally, it could result in ending and replacing costly human inspection, and reduce overall the engineering and maintenance efforts. So what it cannot do, and again, it's very case by case situation. What the capabilities are and how much it fits to your application. But in general, we can say it does not replace applications where high accuracy measurement is required. And it also, as mentioned before, it requires a different approach for system validation, because it's a black box, and you don't have tolerances that you can set in, let's say, in the millimeter world or wherever. So this needs a different approach. So I'm not saying it's not possible, but it definitely needs a different approach. And as usual, and let's say I'm a hardware guy, it does not make high quality image acquisition obsolete. So you still need a good camera, a good lens, a good illumination setup to really see the properties of the product that you're aiming for. It's from my point of view, that's always the key for a good visual inspection, and that can be a challenge by itself. And yeah, last but not least, it's not magic, so it's not the solution for everything. But we hope we were able to demonstrate today that there is a good potential, and we have seen that in the field out there, that there is really added value with the usage of this new technology. So now it's time for a Q&A session. I've seen there is some comments already. So we start from the top and work through them. And just in case you want to find additional information, you can also find that on our website. I will share the link and the QR code afterwards. So let's get started. Scroll to the top. A lot of thank yous, some technical questions about. Okay, first one is which FH controllers support the AI? As I know, Omron has multiple FH controllers. That's correct. So the latest edition is the FH 2050 and the FH 5050. These support the AI tools. Again, it's part of the standard, the standard package, software package that you get, and obviously, within the family. So the 2050 is available in different options. How much cameras you can connect to them, but if you're looking for an AI application, the 2050 and the 5050 is the way to go. Next question is, how does software support fine-tuning? And how does your software support fine-tuning of the model? I think Henrik tried to explain it a little bit. You can definitely define the area of interest, and also detect some abnormalities that you would not consider as a defect part. To really answer that, I think it would need an additional session between us. So at any time, if you're willing to look into the application that you have in front of you, feel free to contact any Omron colleague that is available locally. You can reach me over LinkedIn, and I'm happy to support with all of your questions. Going back down, okay, there's let's say a request for a very specific solution. I think, again, let's take that offline. It's not the audience here to discuss that, but we are happy to do so. Next question I see, is there any plan for multi-class classification? For the time being, not. We, let's say, based on the analysis we made about the use cases in the industries that we are mainly focusing and active on, for now, okay, not okay, classification for the AI is desired. But obviously, you can, if a false part was detected based on the AI, you can implement additional traditional vision tools to distinguish between different types of errors. So again, it's a free element in the FH workflow, and if you reached a non-good result, that doesn't mean this part is automatically out of consideration, but you can in the workflow then analyze it further and not just replace it. Another question: AI supports global shutter and rolling shutter. Yes. So from the type of image acquisition, there's no limitation. It can operate with both our global and rolling shutter cameras that are part of the FH platform. Then there is one question: can we upgrade the firmware to use AI? Yes, that it's possible, but again, we would recommend to use the 2050 and 1050 simply because of let's say resource capabilities of the installed CPU. Then there is a question: do you have any plans to release an AI tool for reading DPM codes? This is currently under investigation. We do think this is also an interesting area to use artificial intelligence-based tools, but it's let me put it this way: work in progress. So nothing we can offer for now, but definitely an interesting topic or an interesting application range to look into. Then there is another question: can AI be applied to measuring unknown complex shapes and volumes? Well, the question is a little bit fuzzy. I mean, measuring again is something that is difficult. So we talk about inspection. Complex shapes, that's a relative phrase. I mean, if you have examples, please feel free to contact us, and we will be happy to look into the details of your application. Otherwise, it's a little bit difficult to answer this question. So if there are, for now, that's the end of the questions that have been raised. There's another one. Any plans to bring AI on the FHV? So the FHV7 is our smart camera that features the same software like the FH controller-based systems. For the time being, same like with the DPM, we're working on an implementation, but it's too early to give you any estimated date on that. But definitely, it would be a desire to also have that great capability on a smart camera with all the benefits that come with a different platform here. Then there's another question: how often does the model have to be retrained, a learning rate tweaked for more complex applications? Maybe Henrik, you can answer that.
Yes, I think that for the model retraining, I think once you have a model that has a good enough representation on your product variation, that should be enough. So we are not expecting to have to reevaluate the model a lot of times. That would happen in the instance that, for example, there are small variations on the product you're producing, right? So you want to incorporate these new variations on your model to make sure that it's going to be working fine. As per the second part of the question, so learning the rate tweaked for more complex application. So okay, so to be honest, I didn't fully show the full capabilities of the algorithm, and it is true that for the learning and optimization, there are a few parameters that you can tweak and change. So you can do some kind of augmentation and things like this to make sure you have a larger data set, actually a virtual data set that you're working with of images. So it really allows you to do a few more parameterization, I would say, to go a little bit deeper. So yeah, I hope this answers the question.
Yeah, again, I think it needs to be evaluated, and yeah, it's difficult to give general answers to these kind of questions. But again, yeah, I can only offer that you test us and get in touch with us in order to find out more details about your application. Then there is one question: are AI tools accessible through macros like the other tools? I think there is no limitation here.
Well, I mean, you are able to get the results and stuff like this. I'm not sure what is actually what you want to do from macros, since yeah, I mean, everything of this tool, you're going to do it pretty much from the interface of this tool, because it's quite visual and you want to see what's happening and how the results are getting. But definitely you have some ways to interact with it from the macro.
I think you can take over the next question as well.
Okay, so yeah, so you repeat it a few times because it allows you to select manually the range of products that you want to use for creating your model, right? So of course, one next step could be to try to automate this step. But what we like now is that you have like a representation of products, and you're selecting the ones that you want to include in your model. And you can also visually check these products to see if there's something that is wrong or misclassified. So it also gives you the opportunity to say to see if there's something misclassified maybe. And yeah, at the end you just add these new pictures to try to make your model more robust. But it's true that in the future, that's one of the steps that we would like to automate a little bit more. So you don't have to look. At the end, it's like maybe for standard application, you have to look around between 2 and 4 times. So it's not a nightmare, but yeah, that's definitely one of the steps we are going to be working on.
Okay, perfect. So I don't see any additional questions. We exactly reached the 45-minute time frame. So yeah, let me thank you for your attention and also the questions you raised. Again, at this point, my offer: reach out to us wherever you are located. I'm sure an Omron office or Omron colleague is close to you. And yeah, we are looking forward to the exchange and interchange with you for the next days and weeks to come. There is one additional question coming. Is there a correlation between the processing time in the AI tool and the number of trained images?
Is there a correlation between the processing time? No, there's not. I mean, once you have the model, it's the model that it's compared against the new images, so it does not make a difference.
Okay. Thank you, Henrik. Thank you very much for attending, and yeah, let's keep in touch. You know how to reach us. Thank you.